Okay. Zoomland, can you see the screen?
Yeah.
Yep.
Okay, so this is integration lecture 2. And so what I want to do today is just, again, a little bit of motivation behind integration and then connect it to the differentiation results that are the next set of problems. So we've talked about derivatives. If f of x is the distance at time x, what does f prime of x represent?
Velocity or speed
Is speed.
depends on what you're talking about.
Right. So if I give you, some curve like this, what I can do is the derivative gives me the slope at this point. So it's the slope at the point is the instantaneous rate of change.
Like instantaneous speed first.
So the instantaneous speed. Okay. So we've talked about this. And what's the fundamental expression? It's f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. So the distance traveled over the amount of time that
Or
elapsed.
wait, what's the other one? The limit is like x goes to a.
Or you could do it as the limit as x goes to a. If you wanted to do this at the point a rather than the point x. And so what you're doing is you're looking at how far you've gone in a small amount of time, and you look and see what that ratio is. And so here, think of this as the time axis, think of this as the distance axis, and then the slope is going to give us the speed. So what we can do is we can look at the inverse of differentiation. And this is integration. So now, if I give you a curve, over here, what I can do is I can have time and I can have speed. And I have some curve. And what I can do is I can look at the area under the curve from A to B. So what do you think the area under the curve from A to B is? Area under curve from x equals A to x equals B is what? So if I look at the area under the speed, what do you think that should give me?
Oh, it's distance because you multiply like speed times time, and it can just give you a unit of distance.
Right. So let's look at the easiest example. So the easiest example is what should be true about the speed. Speed is, okay, 0, more general than 0 is constant, is 1. So c is some constant speed. So if I give you constant speed, then I'm always equal to c. And if I want to know how far have I gone from, say, 1 to 5, well, distance is speed times time. So here it is c times 5 minus 1 equals 4c, and this is the area under the curve, the distance curve. So this is our first example of finding areas under curves and caring about it.
Yeah.
So in this case, the area under the distance curve gives us, the area under the speed curve gives us the distance traveled.
Yeah.
And again, it's often very good to put in labels. This is time and this is speed. So more generally, if I give you instead, let's say I gave you, again, here, I'll do it in blue, who cares? Here's time, here's distance. And imagine, I'm sorry, not distance, I want speed. And so imagine your speed is like this. Okay,
That's weird, but yeah.
so you have discontinuous motion. Could you find the distance traveled?
Yes.
How would you find the distance traveled?
Just do like that.
Add up the parts.
Yeah.
Yeah, we would just
Oh yeah, and what's the deal with the step function?
so
Like, how does that thing work?
How's what work?
a step
The-
function?
Yeah, because I've seen like pictures of it, but I haven't I don't understand it at all.
Okay, so I will give you a little bit more details on that. So what I'm doing here is I can find the area under each place because it's constant speed, right? Is the sum of the different blocks.
Yeah.
Right?
Yeah.
And so in each one, we have constant speed. So we always like to reduce things to things we understand. So we know what constant speed is. So if we just have a couple of blocks of constant speed, then the distance traveled is the sum of the blocks. So here, what we're using is a stepwise function. So what this means is we have a different form for f of x depending on where x lives. So for example, maybe I give you f of x is the following. It's 2x minus 1 if x is less than or equal to 1, and then 2x plus, let's do maybe negative 2x plus 8 if x is greater than 1. So if I try to plot this, it's going to be two lines.
Yeah.
For the first one, what is the key point that we need to understand?
1.
1. So when we look at the point 1, well, when x is equal to 1, 2x minus 1 equals 1. When x equals 0, what do we get?
Minus 1.
Minus 1. So this is going to just be a line with slope negative 1.
No.
I mean, with slope 2. Sorry, with slope 2 with intercept negative 1. Okay. When x equals 1, we use the definition from the top, 2x minus 1. Now, when we look at x greater than 1, what's the value of the function when x equals 1?
6.
6. So it would be all the way up here at 6. And then what's the slope?
Minus 2.
The slope is minus 2. And so over here, where is this going to hit the x-axis? Where does negative 2x plus 8 hit the x-axis at x equals
4.
4? And so if I wanted to just keep drawing the function, I would now have a line coming, it's not such a good line.
You should do it from there.
No, I'll do it from here coming up. And continuing. So this would be the plot of my discontinuous function. I use each region to define it. Is this function continuous? Why or why not?
No.
Okay, so not continuous. We need the limit as x goes to 1 from below of f of x to equal the limit as x goes to 1 from above of f of x to equal f of 1.
Yeah.
And the limit from below does equal f of 1, but it doesn't equal it from above.
But isn't this still differentiable at every point?
No, it's not differentiable at x equals 1.
Wait, hold up.
If you calculate the derivative coming from the left, you would get a slope of 2. And if you calculate it coming from the right, you would get a slope of negative 2. So it is
plus 8. If it was like plus 3,
not,
it would work.
so if we replace the 8 with 3, it would be continuous but not differentiable.
Oh, right, because if you
If-
have the like sharp turns, it means it's
Right.
non-differentiable.
It would be continuous, but not differentiable. Does that answer the question?
Yeah.
Okay, so more generally, if again, this is time and this is speed, if I gave you a curve,
So we'll take a curve.
so I'm doing like a polygonal approximation. So if I gave you something like this for my curve, where it's
take all those
it's a
blocks.
bunch of constant sections, could we find the area under the curve?
Yeah.
Yeah.
See, annoyingly wrong.
So we can find the area under the curve. You know, it's constant in very small windows, right?
Yeah.
And now, if I try to give you, that this is like an approximation to a true curve like this, the hope is in the limit, we can find the area under the smooth curve. Okay?
Yeah.
So integration is the inverse of differentiation. Integration is the inverse of differentiation. So if I start off with a function f of x, I can calculate its derivative f prime of x. So let's just write a few. If I give you x squared, what's the derivative? 2x. If I give you x to the n, what's the derivative?
To n minus 1.
Okay.
That, right?
Yep. Does it matter what n is?
No.
Nope. As long as n is not 0. But even if n is 0, then you can say that's just 0. If I give you sine of x, what's the root of sine of x?
Cosine.
Cosine of x. Now if I give you e to the x,
E to the x.
I give you e to the x. Okay.
Yeah.
Now what we could do is I could give you a function f of x, and I could ask for the integral, and we'll write it as big F of x. So what this means is we want a function such that the derivative of big F is equal to little f. So if I give you now the function x squared, what function has derivative x squared?
1/3 x cubed.
1/3 x cubed. If I give you the function x to the n, what function has derivative x to the n?
1/n+1 x to the n plus 1.
Do we have to be careful?
Yes.
What do we have to be careful about?
If n is minus 1.
Yeah, need n not to be minus 1. Does anybody remember what has derivative 1 over x?
Ln.
Very good. The natural log of x. And what function has derivative e to the x?
E to the x.
E to the x. So what we can do is we're assembling a list of functions. So the derivative of big F is little f. So we use the notation big F to make it easy when we look down to remind ourselves that it's related to the function little f. So let's say I give you a function f of x, and I calculate its derivative, and then I calculate the integral of f prime of x. What should the integral of the derivative of f prime of x be?
F of x.
It should be f of x. So let's say we start off with x squared. What's the derivative?
Like 2x.
2x. And what function has derivative 2x?
X squared.
We've got to be careful. Does anything else have derivative?
Plus a constant.
Yeah, plus any constant. So they're not completely, we got to be a little bit careful. When we talk about the integral, there's more than one integral, If there's an infinite number,
But it's the world famous C, so it's just plus C, right?
right. So we'll talk about this in greater detail throughout the semester. If I give you x cubed, what function has derivative x cubed? I'm sorry, what function?
Yeah. Don't you mean what
function? What is the derivative of x cubed?
3x
X to the fourth over 4.
The x
Wait,
squared.
never mind. That's the other
Right.
one.
And then what function has derivative 3x squared?
X cubed.
6x.
Plus
Wait. Derivative or antiderivative?
I'm sorry, antiderivative.
I know what you meant.
So I said the wrong thing, right?
but I
Cam,
know-
you got it wrong.
No, you weren't reading his mind.
So integral is the
Yeah, I
same
have-
as the antiderivative. So what this is telling us is we need some notation. So if I give you, y equals f of x for the derivative, we often write y prime or f prime of x. For the antiderivative or the integral, we write big F of x, or we write the integral, so this is called the integral sign of f of x dx. So there's a lot of things going on here. So this is the integral sign. What letter does it look like?
So,
S for summation.
Yeah, S for sum, or for Steve. No, probably sum. And over here, the dx this is telling us what is the variable. So another way of writing f prime of x is this is dy dx or df dx. It's telling us that we're taking the derivative with respect to x. X is the variable that changes. So x is the variable. And so when we're writing the integral, this is telling us what we're taking the integration with respect to. So the last thing I want to just do, I just want to introduce notation today, is if I give you some curve, we want to find the area from A to B. So note, this is going to be notation. So the integral from A to B of f of x dx means the area under y equals f of x from x equals A to x equals B. And so we've talked a little bit about this before. We talked about the fundamental theme of calculus.
So wait, can you use the fundamental theorem of calculus to solve all definite integrals, or are there like limitations?
Well, the problem is we have to be able to compute the antiderivative. So the fundamental theme of calculus says the antiderivative gives you the area. So this is a huge result. This is the fundamental theorem of calculus. If little f is nice.
Are there multiple fundamental theorems of calculus? Because I think they said there was like the first one and the second one in the book.
They have slightly different forms. They matter a ton. So the fundamental theorem of calculus says that the area under the curve from A to B is the antiderivative at B minus the antiderivative at A. And you can use any antiderivative you want, because if they differ by a constant, since you subtract, that constant cancels. So this is content. This is the theorem. This is the meat. This part over here is a definition. This is a definition. And over here, this is a theorem. So the theorem is that the area is equal to the area under the curve. And so when we use this to just write this down, we don't initially know that this is related to the antiderivative. It would be bad notation if it isn't, because we're using the integral sign to denote area. So for example, if I now give you, say, the function f of x equals x cubed, and I ask, what is the area under this curve from 0 to 1? So what function, can you give me a function that has derivative x cubed?
1/4 x to the 4th plus c.
Plus any constant c. So let's take c equals 0.
Okay.
So then the integral from 0 to 1 of f of x dx, this is the area under f of x from 0 to 1, is big F of 1 minus big F of 0. So that's going to be 1/4 1 to the 4th minus 1/4 0 to the 4th, or just 1/4.
Okay. Wait, one quick question. I've heard that like when you have definite integrals, you kind of like ignore the c, or you use it, or it matters in a different way.
Well, so let's expand on this remark. So let's say I give you a function. Let's take the one we have. F of x is x cubed. So one antiderivative is 1/4 x to the 4th, and another one is, say, 1/4 x to the 4th plus 8.
Yeah.
If I look at big F of b minus big F of a, this is 1/4 b to the 4th minus 1/4 a to the 4th. If I look at g of b minus g of a, this is 1/4 b to the 4th plus 8 minus 1/4 a to the 4th plus 8.
So the h just gets.
Do you see how the 8s cancel?
Yeah.
That's why it doesn't matter.
And so you will then get that this is also 1/4 b to the 4th minus 1/4 a to the 4th. The c
And
does not matter.
wait, then would you have to like add the 8 back in based on
No,
like
No, it doesn't matter, Z.
it's like potential energy.
It's you add 8 and then you subtract 8. It does nothing.
right, but like if you had a curve, if you're wait, never mind, that would have an x. I was saying like if your function was x cubed plus 8, I guess then the antiderivative would be x to the 4th over 4 plus 8x. So never mind.
There are many antiderivatives, but if you are antiderivatives of the same function, your difference is the same. So if big F prime of x equals big G prime of x equals little f of x, then big F of b minus big F of a is big G of b minus big G of a. If you have two functions that have the same derivative, then if you look at their difference at b and a, it doesn't matter which one you look at, because all we're doing is we're shifting the plot up. So if you look at so we had, say, big F of x was 1/4 x to the 4th, and big G of x was 1/4 x to the 4th plus 8. Yeah. So for the first one, here's maybe big F of x. And then here, shifting things up by 8, here's big G of x. And so if I take any 2 points A and B, and I want to look at the difference between f of b minus f of a, that's going to be the same if I extend it all the way up here.
And it doesn't matter that you're 8 units higher.
It doesn't matter that I'm 8 units higher, because it's 8 units higher for both.
Yeah.
So this distance here and this distance here, these are the same. because all we're doing is we're just shifting the antiderivative up by 8 units. So if we add 8 units to f of b and we add 8 units to f of a, then the difference of f of b and minus f of a hasn't changed. Does that make sense?
Yeah.
Okay, so I'm going to skip because it's getting a little bit late. The application of, we care about this through probability. I want to just talk about differentiating inverse functions. So the book uses notation that I don't love as much. So we did, let's say a of x is f of g of x equals x. So f and g are inverse. We can calculate a prime of x two ways. If we use the chain rule, we get f prime at g of x times g prime of x. And what's the derivative of x? 1. So we get g prime of x is equal to 1 over f prime of g of x. So I love putting in lots of different names for functions. The notation the book is using is a bit more concise. They use dy dx is 1 over dx dy. If you think about what's going on formally, just multiply by 1. And how would you write 1? We can't quite do this as just dy over dy. And if you have 1 over dx dy, and this is illegal, and you multiply by dy over dy, what can you do to the dy in the denominator? Cancel it. And you would get dy over dx. So this is a way to remember that if you have dy dx, then dx dy dx is 1 over dx dy. So why do we care about this? So the idea is if we know the derivative of a function, we know the derivative of the inverse. And so let me just do one example from the book and then we'll call it a night. So let's consider the function if f of x equals x squared, find the derivative of f inverse. Let's see. I'm trying to see if there's a better one with notation. Okay, find a derivative for the inverse of y equals, is that x squared minus 1?
Yeah.
Okay, so let's say we're given that y equals x squared minus 1. I like to view this as y of x equals x squared minus 1. So what's y prime of x, which we can write as dy dx?
2x.
It's just 2x, right?
Yeah.
So we know what the derivative of y is. Can we solve for x in terms of y?
Yeah.
Yeah. So if y equals x squared minus 1, then x squared equals y plus 1. So x is equal to plus or minus the square root of y plus 1.
Yeah.
So we have to choose, are we on the positive part or the negative part?
Positive.
All right, so say we take the positive part, so x is equal to y plus 1 to the 1/2. Then what is dx dy?
1/2
1/2
y plus 1
y plus 1.
to the minus 1/2.
And then what's the derivative of y plus 1?
1.
1. But y plus 1 to the minus 1/2, well, if x is equal to y plus 1 to 1/2, this is then just going to be 1 over 2x. Does everyone agree with that?
Yes.
Zoomland, do you agree?
Wait a minute.
Since
Oh yeah, that makes
equals
sense. Y plus one
y
to the,
plus 1 to the half.
yeah, that makes sense.
And now if we use dx dy is 1 over dy dx, we would get dx dy is going to be 1 over dy dx. What's dy dx?
1/2 y plus 1.
Nope.
Wait.
What's dy dx? That's dx dx.
Oh,
2x.
It's 2x.
sorry.
And do you see how these
I thought you
agree?
said the other thing. Yeah.
So these agree.
That's good.
It's good. So it's just a question of how do you
Really
want to
wanted
compute it, right? If you can solve for y in terms of x or x in terms of y, it makes it very easy to compute. We could also try to do this using implicit differentiation. Now, there's lots of ways to solve problems. We have y equals x squared minus 1. View x as a function of y now. So we have y equals x of y squared minus 1. So take the derivative with respect to y. So we want to calculate the derivative with respect to y, d by dy. What's the derivative of y with respect to y?
1.
1. What is the derivative of x of y squared with respect to y?
2y.
Not
No.
2y, 2.
What is that?
We have x of y squared. What's
2xy.
2x of y
I was just going to say what?
to the 2 minus 1,
Or to the 1.
or to the 1, times what?
1.
Not 1.
What?
Zoomland, what goes after? We're doing the power rule.
Yeah.
If I give you f of x squared, its derivative is
2
2,
times the derivative of y.
not the derivative of y.
X1.
It's the derivative of x of y,
Okay.
plus x prime of y. And what's the derivative of 1?
0.
0.
So we get 1 equals 2 x of y, x prime of y. So solving, we get x prime of y is 1 over 2x of y. So we're trying to view now x as a function of y versus y as a function of x.
I thought it was like x times y.
No, it's not x
No,
times
I
y.
know.
Yeah,
That's
it's
what I was
x.
thinking. That's why I said
Right.
that.
So again, there's lots of different ways to do this. You should look at what's going on in the book. This is around page 156, and we'll discuss these problems later. There's multiple ways to do problems like this.
Yeah.
And depending on how you do it, some ways are going to be easier than others. For me, I think it's much easier if you put in very explicitly what the argument is. So if I'm viewing x as a function of y, I write x of y. If I'm viewing y as a function of x, I write y of x. Right. Any questions?
No.
Okay. And then the last thing, and I guess just we got like 10 seconds left, so I'll just quickly say this. If I give you some curve like this,
Yes.
and let's say the area is 1 and the function is non-negative. This gives us probabilities. And this is one of the reasons why we care so much about finding areas under the curve. So if I give you A and B, this will give us the probability we have a value between A and B. And so we'll talk a lot more about this later. But in my mind, anytime you take a calculus class and the teacher never mentions the word probability, you can actually sue them for violation of a mathematical contract as to why do we care about this? We care because we can use these to calculate the odds of things happening. And it turns out that in many situations, we can come up with functions that are amenable to calculus, that we can find the antiderivatives and we can calculate these probabilities very nicely. All right, have a good evening all.